Okay guys, we're in section 5.3 and we've already discussed one of the pieces of our fundamental theorem of calculus that we can integrate, find the antiderivative from A to B. But there's a second piece. Before we do that second piece, I want to kind of ask you a few questions. What happens when I square a square root? Or what happens when I multiply something by 2 but then divide it by 2? Aren't those kind of inverse functions of each other? They cancel each other out. And so what do you think would happen if I integrated, I took the antiderivative, but then I differentiated it? Well, wouldn't I kind of get back to where I started? Doesn't that kind of make sense? And so the second piece of our fundamental theorem of calculus says that if g is the antiderivative of f, then I take the derivative of g, I end up just getting f. So an antiderivative and a derivative are inverse functions of each other. They kind of cancel each other out. Okay? So we're going to kind of walk through that process a little bit so you can kind of see that they are inverse functions of each other. So I want you to look at example number 3 with me. It asks us to evaluate, and so we have a few different pieces, kind of notations here. It asks us to take the derivative of this integral, or the derivative of the antiderivative. Well, when we think about it, if I square a square root, if I differentiate an antiderivative, we should end up getting back to where we started. But let's walk through the long way and see if that actually is the case. So let's do it the long way by actually integrating this piece first. We should know how to do that using our fundamental theorem of calculus. So if I give you the integral of 3t from 0 to x, we should be able to use our integration rules, add 1 to the exponent, and divide by that exponent. So I have 3t squared over 2, and I want to evaluate it from 0 to x, right? Okay, and so if I plug in an x, if I use my fundamental theorem of calculus, I plug in an x, and then I plug in a 0, and I subtract, don't I end up getting this 3x squared over 2? So that's this piece here. But now I need to still take the derivative. So I integrated it, but now I need to go back and take the derivative. So now we have to kind of switch our brains back and forth, and now we have to take the derivative of 3x squared over 2. Remember, derivative rules say that I should be able to take this exponent, bring it forward, and get a new exponent by subtracting 1. So if I bring that exponent forward, the 2 in the numerator and the 2 in the denominator reduce, and if I subtract 1 from the exponent, my new exponent is 1. So I end up getting a derivative now of 3x. Well, is that what I started with? I started with the 3t, and I ended up with a 3x. Really, really, really close, right? What was the only difference? Well, the only difference from where I started to where I ended was that my variable changed. My variable started with t's, but ended with x's. But the function was the exact same thing. I integrated and then differentiated, and they ended up kind of canceling each other out, right? Let's do another one. If I look at B here, it gives me big F. It says that big F is the antiderivative, or the integral, but then I want you to take the derivative. I want you to take the derivative of the antiderivative. Let's do it the long way. So I want you to integrate first, take the antiderivative. I don't know about you, but that looks like a product rule, and so before I do it, I'm going to have to distribute that t through. I end up getting a t cubed plus t. So let's go ahead and find the antiderivative. I ended up getting t to the 4th over 4 plus t squared over 2. Using my fundamental theorem of calculus, if I plug in x's and then plug in zeros and subtract them, did you get a big F of x to the 4th over 4 plus x squared over 2? So that's my big F. That's the antiderivative. Now I want you to take the derivative. We just took the antiderivative. Now I want you to take the derivative. What is the derivative of x to the 4th over 4 plus x squared over 2? Well, you should end up getting x cubed plus x. Well, is that what we started off with? Well, kind of. If I were to factor out an x, wouldn't I get an x times an x squared plus 1? Which is similar to what we started with. The only difference is my variable changed, right? Just like in the first one. My function is the exact same function, just my variable went from a t to an x. All right, I want you to look at 2 more with me in this video. I want you to look at C and D. And so C looks a little bit different. One, because it's trig, yes, but what's another difference that you see in part C? Well, I don't know if you've noticed, but in part A and part B, my limits of integration were from 0 to x on both of them. And on this one, it goes from pi over 4 to x. It's still asking me to find the derivative of the antiderivative. So we should still get back to where we started. Let's see if that pi over 4, though, makes a difference. Let's do it the long way first. So let's integrate secant squared. So what's the integral of secant squared? Yeah, you should get tangent. We're going to evaluate it then from pi over 4 to x. So let's plug in x. Let's plug in pi over 4. I end up with a tangent of x. And then what is pi over 4, tangent of pi over 4? Isn't that 1? And so that's my antiderivative. And now we want to take the derivative. And so then what is the derivative of tangent? Secant squared, right? And what's the derivative of 1? Isn't it 0? So did we end up back to where we started? Yeah, it's the same exact function. It's a secant squared, but instead of a t, it's an x. So it looks like that lower limit doesn't matter. As long as it's a number and you go up to x, then you should always end where you started with, just with that x plugged in. And so instead of doing it the long way on all of these, as soon as you notice that you're taking the derivative of the antiderivative and your limits are from a to x, a number up to x, then you should be able to skip all of these pieces and be able to say, well, if my original function was 3t and I'm going from 0 to x, well, then my answer for the derivative of the antiderivative is just going to be 3x. If my original function was, oh, it's not working here. Sorry, guys. If my original function was t times t squared plus 1, and I'm going from 0 to x, and I'm differentiating the antiderivative, well, then I'm automatically just going to end up at the same place that I started, just with a different variable. Okay? So look at D with me. If I asked you to do this derivative of the antiderivative, hopefully we recognize the derivative and the antiderivative are just inverses of each other, right? Why square a square root if they just cancel? If I asked you to do it the long way also, wouldn't you be a little bit stuck? Because this t squared plus 1 to the 1/2, isn't that a chain rule? And we know that there is no such thing as chain rule. So you actually can't do this problem the long way. That's why we need to be able to recognize that the derivative of the antiderivative are really just inverse functions of each other, and you should end up back where you started, just with an x instead. So instead of doing all of that work, we could say that the derivative of this integral, the derivative of the antiderivative of 0 to x, is really the square root of x squared plus 1. Remember that t changes to an x. Okay? So I need you to be able to recognize that second piece of the fundamental theorem of calculus so that you can go straight from the beginning to the end without having to do all that work, especially for integrals that we don't know how to do yet.